Hello, everyone, and welcome to today's Bright Talk presentation entitled A Deep Look at New Memories. New memories like MRAM, ReRAM, phase change memory, FRAM are vying to replace embedded flash and eventually even embedded SRAM. Are there other memory technologies threatened with similar fates? What will the memory market look like in the next 20 years? My name is Arthur Sainio. I am the co-chair of the Persistent Memory Special Interest Group within SNIA. Our speakers today are Tom Coughlin and Jim Handy, who are with me now. Tom Coughlin is a leading digital storage analyst and technology expert with over 40 years of industry experience. As president of Coughlin Associates, he provides market analysis and consulting services in digital storage and emerging memory technologies. An IEEE Life Fellow and the 2024 IEEE President, Tom is a prolific author and contributor to Forbes.com. He holds 6 patents and has organized major industry events, establishing himself as a respected figure in the digital storage and emerging memory technology sectors. Tom holds degrees in physics and electrical engineering. And also presenting today is Jim Handy. Jim is a seasoned semiconductor industry expert with over 35 years of experience. As the founder and general director of Objective Analysis, he provides market insights for the semiconductor and storage sectors. Jim's career spans roles at tech companies and analyst firms. He is known for his technical expertise, accurate forecasts, and frequent contributions to industry publications and events. Jim holds degrees in electrical engineering and business administration. Say hi, guys.
Hello there.
Hi. Looking forward to this.
Indeed.
Should be very interesting. A little bit about SNIA. SNIA has 200 corporate members, approximately 2,500 active contributing members, and more likely more than 50,000 worldwide IT end users and professionals. SNIA's role is to engage and educate the industry, accelerate industry standards and new standards, and also propel technology adoption. We do that through many methods, one of which is this Bright Talk today. So we hope this will be beneficial for everyone. A brief notice here about our copyright information. I'm not going to read through this, but it will be posted in the slides after the presentation. Also, another couple of reminders here. We would like you to rate this presentation. I'll remind you at the end to do that. We'd also like you to ask questions and type those in the chat area. We'll be monitoring those. We do have time for questions at the end. And yes, please give us your comments. And with that, I'm going to turn it over to Tom and Jim.
Well, thank you very much. And thanks to SNIA for letting us talk to you today. And for all those who were able to join us either live or perhaps later on as a recording. So here's the agenda of our talk. First of all, we're going to discuss the motivation for people looking at new memory technologies, especially non-volatile memories. Then we'll talk a bit about those non-volatile memories, MRAM, resistive RAM, phase change memory, ferroelectric random access memory. We'll look at how this market is developing, what are the obstacles facing for these becoming mainstream, and which applications are going to be growing in. And finally, a look towards the future and an eventual displacement that we are projecting will occur from dependence upon volatile memories, which can consume a fair amount of energy, and non-volatile memories, which we believe eventually will be able to replace many of these volatile memory technologies. So let's go to the next slide and talk about what are the motivations for looking at these new non-volatile memory technologies. So there's a couple of types of memory that are used in a lot of the embedded applications that you use every day, whether on devices that you carry with you in your car, in your home, and industrial and even enterprise applications. So the first one is NOR flash. NOR flash is an embedded memory that is used primarily to store things that need to be accessed to get a device working. So the code that's used to boot up a system, for example, are stored in NOR flash. NOR flash is a flash memory. Therefore, it is subject to wear out from writing on it. So that's another potential concern for some applications, particularly where you update that data often, which is online updates are becoming more and more frequent in many consumer and embedded devices. The other type of memory that we need to look at here is the static random access memory. This is the cache memory that's used in many applications. You can see here in a microprocessor. Of course, the embedded NOR and the SRAM have rather regular features. You can really see where it sticks out in the chip. You can see in this case, for instance, and it's often the case, that this static random access memory, which is where you store the data that you're actually the data just before you're actually working on it, takes up a fairly large amount of the chip. So there's issues that we're running into with embedded NOR and SRAM, again, used in all kinds of devices every day. Embedded NOR flash stops scaling at 28 nanometers, and that's because there's no NOR for embedded devices when they go to the FinFET processes, say at 14 nanometer and smaller. So there's three choices of what you can do. You can shrink the rest of a chip, but not that NOR flash memory. For instance, combining a 10 nanometer logic with 45 nanometer NOR, which then takes up a lot of real estate in the chip. You can use an external memory, external NOR for device, for example, as well as the chip that contains everything else. Or you can move to using some new type of memory technologies, in particular, the non-volatile memories such as MRAM and resistive RAM, or some of the other options that we spoke of that we're going to be talking about. In addition to NOR flash, embedded SRAM isn't scaling in pace with the process shifts. Now, one thing you should know about this SRAM is it's a fairly large memory cell. It's volatile, but it uses something like 5 or 6 transistors, for example, in order for it to operate and do what it does. And it's not scaling, in addition, in pace with the process shrinks. So processor caches are going to consume, if you continue to use SRAM, a growing share of the CPU die area. And that's expensive real estate. It's things where you could, if I had more memory, it could be useful, or I could put in other processes or other processing or other capabilities on the chip. So embedded SRAM scaling is slower than logic scaling. You can see an example of that here, shown representatively in terms of the cell area versus the process geometry. We show, this is again from Jim's objective analysis. You can see the logic processes continues to shrink the cell area required for the logic, while the static random access memory is not shrinking as much. So it takes up, for a given amount of memory space, it takes up a larger amount of the chips. And now I'm going to pass you on to Jim for the next set of slides.
Thanks, Tom. So we also need a problem not just with the embedded memories that Tom talked about, but also with discrete memories or standalone memory chips. New memories can scale past DRAMs and flashes limits. And this is a graphic that shows how we've run into problems. With NAND flash, we ran into kind of a brick wall at 15 nanometers, and the industry had to go to 3D NAND. Had 3D NAND not been devised, then we would already be shipping probably very high quantities of one of these alternative technologies as a planar type thing. But NAND has gotten itself some extra life with 3D. NAND's unique in being able to do that. With DRAM, 10 nanometers seems to be the limit. The current technologies that are being shipped are 1X, 1Y, 1Z, 1A, 1B, and it goes on from there. But they're all, the one in front of them it means that they're all somewhere in the tens to teens. And it doesn't look like there's going to be a way to be able to shrink the DRAM cell the way that we know it any further than that. And so we're facing a limit there. There is some talk about 3D DRAM, but 3D DRAM would be far more difficult to pull off than 3D NAND, simply because of the fact that the DRAM cell has kind of been 3D ever since the 1990s when it went into trenches. And then finally, we have new memories, which can pretty much go to beyond any of the known limits of what we've got today, because these all shrink very well. And so you can see that there's some attraction to going to that with, if we were stuck with planar NAND, we'd already be there with a new memory. With DRAM, it's very likely that it's going to go to a new memory, and there's been a lot of talk at industry conferences about what that new memory might be. One extra benefit of these memories is that they're persistent. Persistence is something that doesn't exist in DRAM, and writing to NAND flash or NOR flash is a very slow process and takes an awful lot of management. But we do see these other memories as being very simple, that they're bit rewritable, and they're pretty fast in the write cycles. And so we do believe that persistent memories will someday prevail. Intel did try that with their Optane, and they had problems with the difference between price and cost, that they had to sell it at a lower price than what their costs warranted. And that ended up causing Intel to decide to phase out that business. We believe that scaling issues, when we get to very small process geometries, will cause that problem to go away, simply because of the fact that you'll be able to make much smaller die sizes, and that will end up getting the costs out. SNIA, during the work to put together Optane, and even before that, laid some very solid groundwork for persistent memory. And that will become invaluable at a later date, even though it isn't currently used in a widespread way. It is used with Optane-based systems still, but not in many more. We do believe, too, that as Tom was talking about the embedded SRAM problem, cache memories will become persistent, and that also will avail itself of SNIA's work. This will cause systems to become much more resilient to power upsets, because of the fact that the registers won't need to be reloaded. The cache will have current data in it when it comes back up from the power failure. And also, because of the fact that these memories can be powered down at times when they're not being used, there will be great power savings in these systems. So there are just all kinds of benefits with these. And so let me talk a little bit about what these memories are. And this is just going to be a very simple overview. We've got MRAM, and I've got these two magnets on the top and bottom of a GMR sandwich, I call it. The GMR is a giant magnetoresistive structure that its conductivity depends on whether the magnet on the top and the magnet on the bottom are pointed in the same direction. Now, you can write to it by just changing the direction of that top magnet, which is represented by the animation. The bottom magnet, which is called the pinned layer, stays from the time that it's manufactured in one certain magnetic configuration. And so then the difference between the several different kinds of MRAM that there are is in how you program that top layer. How do you flip it? And you can do it with a transverse field or with spin torque transfer to get STT MRAM. Or there's a new technology that hasn't really seen commercial use yet called spin orbit torque, or SOT MRAM. And there are several others. They're right now being manufactured by Everspin, who makes discrete or standalone parts, and then TSMC and Samsung in their foundries have MRAM. The next one is resistive RAM, and this works by a conductive or a non-conductive path, and that's represented by the animated things here, is that path either gets closed or it gets opened up in a very minor way, depending on how electrons flow and push the atoms around inside the structure. There are three common approaches for that. One is by moving around oxygen vacancies, which silicon dioxide is an insulator, and if you pull the oxygen out of it with electrons, then it ends up becoming a conductor, and you can make that conductive path represented by the white balls. You can also have a conductive filament. A popular material for that is silver, and you'll actually have one of these black plates. The top black plate would have, which is an electrode, would be a silver electrode, And then those white balls would be silver ions that are moving around inside an insulating material. There's also something called a bulk mechanism, which I won't really go into here, but it changes that entire gray portion into a conductor or an insulator. Most of them require new materials, but some do use standard silicon. A good example of that is Weebit, and Crossbar also has got a standard material. And so you do see these, and they are in production by Fujitsu with a microcontroller. Weebit Nano has got commercial processes available in foundries, and Global Foundries is also shipping certain products that are based on that. The next is phase change memory, and it was hard to put together an animation for this, but this circle is supposed to represent a change in phase with phase change memory for how the material works. They're based on something called a chalcogenide glass, and something that is kind of magical about this material is that if you melt it and then you freeze it slowly, then it freezes into an amorphous state. If you freeze it quickly, it freezes into a crystalline state. And the crystalline state is conductive, the amorphous state is non-conductive, and that ends up causing it to be a 1 or a 0. What's interesting about this is that the same material is used in selectors for MRAM, resistive RAM, and ferroelectric memory. And so that could push this material into volume production and make it something that would be a good candidate for just being a memory by itself. Intel Optane used this technology, and STMicro is the other big proponent of it. They've got a microcontroller that whose memory is based on this instead of NOR flash. But Samsung and Micron have also played in this business. The next one is ferroelectric memory. And the thing about ferroelectric memory is that it uses a certain kind of a crystal that has an atom that can either be in the upper position or the lower position. And depending on which of those positions it is, then it can be used for the gate of what's called a FEFET, a ferroelectric FET, to change what the threshold voltage is. Or in older parts, you could actually tell which way the chip was programmed by trying to reprogram it. So it was a destructive read cycle. But the trouble with the older materials, which are called PZT and SBT, is that they didn't scale. They had problems with step coverage and that sort of thing. And so they were going to be phased out. And then in 2011, somebody at Dresden University found out that you could use hafnium oxide, which is very widely used in today's logic processes, as a ferroelectric material. All you had to do was dope it the right way with zirconium. And they're wrestling with the doping problem right now. But that does look like something, because it's in volume production without the doping, it does look like it would be a relatively easy transition to turn ferroelectrics into that. It can also be built using a 3D NAND structure, which means that it could be built for a price that was comparable to 3D NANDs. Not better than 3D NANDs, or at least, we don't have any visibility into a way to do that now, but still it gives it the ability to be a much faster writing and lower energy write technology that could have the cost structure of NAND. It's being researched by Infineon, Fujitsu, Intel, Micron, an awful lot of companies. And, I think that it's probably going to be a little bit slower to get off the ground than some of these, but it is it's a very promising technology. But something interesting about these memories is that they all share certain key attributes. And so let's run through those one by one. The first one is that they're radiation tolerant, and that's really good for certain applications because they can be used in space, and they end up out in space. There's an awful lot of radiation, and they can do well in those applications, not losing bits. They're non-volatile, which is always a plus, and so that makes it even better. They write much faster than flash, which is, the non-volatile alternative to them. And so, wow, it just keeps getting better here. And they're byte writable. You don't have to do page erase and or block erase and page write. And you can write in place. You can actually write over old data. And so, that makes it really attractive. And they're scalable well beyond 28 nanometers, which is what I was talking about before. And so that means that the cost structure is going to get really good. And so there's just a lot to love about these. And they're all made with innovative materials. And that's actually just a deal killer for most things. So I have this little grumpy face on here for that. That's the thing that has kept these memories from actually getting into mass production.
And thank you, Jim.
Yeah.
So let's look at how this market is evolving. So we believe that the new memory revenue growth is going to be much higher than DRAM or NAND flash. There's just so much potential demand for a non-volatile memory that can fill some of these areas for initially, for instance, where NOR flash and SRAM are going to become economically non-viable. But ultimately, since they're growing so much, if they can continue that growth into the future, they could be threatening DRAM and NAND flash, especially on the DRAM side. If performance improves as well, and there are technologies that are making some of these non-volatile memories start to approach the capability of DRAM. In NAND flash, it's going to be a matter of volume, and can NAND flash continue the scaling that it's been doing? It's been slowing down some from where it was just a few years ago. So there's good possibilities here that these new non-volatile memories, we believe, could become a significant part of the entire memory market. And let's look at some examples of where this is happening. So at the MRAM forum that was part of the IEEE IEDM conference in December 2024, there was a presentation made by someone from TSMC. We've redrawn the chart they were showing here. This particularly was looking at, automotives are increasingly becoming rolling computers, if you will. And there's something called a software-defined vehicle. And there's been demonstrations of that, for instance, at the Consumer Electronics Show this year in Las Vegas. It includes over-the-air software updates. So in this case, you're doing frequent updates over the air in an automobile application. And for NOR flash, because there's limited number of writes you can do, the MRAM and technologies like that seem to be attractive. So NXP example, for example, has been working with qualifying their chips that are using MRAM in processors, these software-defined vehicle processors, and the actual parts being manufactured by TSMC. They're working on qualifying those with major automotive manufacturers. And you can see here on this this slide, representative slide from the MRAM forum, that this includes a 5 nanometer structure, MRAM structure, that can be either flash-like, the NOR flash-like, or if there's ways of making this having higher performance, for instance, faster writes, that can emulate the characteristics of a RAM, like a DRAM type of device as well. So the technologies are developing. This is one example on the automotive side for the use of emerging memory technologies, in this case MRAM, in future applications. So you may very well be seeing MRAM being used in automotive products by, say, 2026 or 2027 as part of the new wave of automotive technologies. Another example, there's there's a company called Ambic, which has a TSMC manufactured chip that uses MRAM as well as some SRAM, but a lot of MRAM in order to be able to store weighting functions for artificial intelligence on low power devices. For instance, they're being used in, you can see a number of smart watches, fitness trackers on the right hand side there. Also at the CES show this year, there was a company called Think AR, augmented reality, AI lenses that were using these in smart glasses that give you a augmented reality experience. They can show you data on the glasses themselves. I think these had something like a 10-hour battery life, and was an application again using that Ambic chip. Although they were not able to tell us the companies that were using this, apparently conventional hearing aids are pretty expensive. They have to run at low power. In order to do that, they make very customized ASIC chips. But the Ambic folks said that there's a number of companies that are coming out with lower cost hearing aids that are using their chip. They can get low power because they're using the MRAM rather than some other volatile memory technology in order to be able to store the information, the weighting functions, for example, in voice recognition capabilities on this chip in order to provide the hearing aid. This gives them the capability of running at much lower power and not having to make a customized chip to enable that. So they see this as potentially an enormous advantage for making lower cost but very effective hearing aids in the future. So another example of the use of these emerging memories. Again, MRAM seems like there's the most examples right now, but in this case, for consumer wearable products, things that are basically giving us capabilities, augmenting our current capabilities. In addition, there are to an industrial automotive, there's also enterprise applications. For instance, there's multiple aerospace applications that are being worked on, satellite memories, radiation hard FPGAs, and space-based neural networks that have been going on. But they're also, IBM uses MRAM as a cache for data in flight in their flash core modules that are used in their SSD-based memory systems. So these are just a couple of examples on the enterprise side. There's going to be more, and there are more in development. And in general, again, it's focused on the MRAM, but it's showing that these emerging non-volatile memories, whether it be MRAM or resistive RAM, or some of these other technologies, that they're starting to show up in devices we use, whether it's personally or in data centers and enterprise applications. So what obstacles, though, do these memories face? Let's take a quick look at that. So memories are chosen by their characteristics, but especially if you get in these consumer industrial applications, by their cost as well. And few systems can justify a higher cost for even a significant technical advantage like radiation tolerance, the low energy or fast persistent writes. So in sole sourcing, just getting it from one vendor is also a significant deterrent to new designs. So whatever you do, it needs to be something that they can find from more than one source. And although you might be able to get more done on a smaller die size, it does not automatically lead to lower cost unless you're making enough of the chips that are using this smaller die size in order for that to become an important factor in terms of the total cost. Intel ran into this problem that they could never get their manufacturing volume of wafers with the Optane memory up to the level where their cost of manufacturing would be less than the cost they had to sell for in order to develop the market. It was an intense effort, but it's just, I think it shows the thing that you're running into and trying to introduce these new technologies, in particular if you're trying to make a standalone memory. It's a bit different in the case of these embedded memories. And that's part of the reason why we think these embedded memories are where these technologies are going to have their greatest growth, at least for the next few years. Now, NAND also went from a period of time where it was more expensive than DRAM until it became less expensive. And it wasn't until it reached enough manufacturing volume that it could do that. And that was back around, I believe it was 2004 or something like that, if I remember right.
Yes.
Nodding.
Yes.
So getting these things, especially on these standalone applications, to the volume where the cost of manufacturing is less than the cost they have to sell at for especially non-specialized application, requires a certain amount of volume. None of these technologies that we talked about are yet at that phase, but they are finding inroads in these embedded applications. We believe that will build up this volume and eventually bring them to that maturity. And Jim, you're going to follow on with this.
Yes. Thanks, Tom. So if I can get the slide to advance. There. So I'm just going to give a little bit of an outline about what we see happening in the future towards 2034 and even 2044. So we're really looking way out there with this. And so this is a very rough timeline about how we see things going. And with embedded memory, we're already there. We've already got MRAM being used in those applications that Tom talked about, the embedded ones, the hearing aids, AR glasses, and wearables. And we're expecting to see that transition continue on. It will be a really slow transition because of the fact that there are an awful lot of legacy semiconductor process nodes that are not going to be replaced. The microcontrollers or whatever it is are not going to be replaced with more leading edge process node microcontrollers anytime soon, simply because they don't need extra functionality that you would get by having a tighter process. And so because of that, it probably will be well after 2034 before we see the NOR and SRAM markets give way to an embedded new memory. And when I say give way, I mean completely. With discrete memory, we think that the transition is going to start a little bit slower, but it will be a little bit faster of a transition. That with discrete memory, standalone memory chips, then the chips can be swapped out from one to the other depending on cost. And that's going to be the case when a new memory comes in. And so that transition should be faster. But because of the fact that DRAM and NAND flash have extraordinarily low cost structures today, that makes them a much harder target to hit. And then finally, memory chiplets. We're expecting, first of all, for the memory chiplet market to remain pretty small, which it has been, up until sometime after 2034. Mostly because of the fact that HBM is well adopted, but we don't see external cache chips being well adopted quite yet in chiplets. And that's a place that's really going to be catching on in the future. So that will be also probably a pretty rapid transition when it happens, but that transition will happen pretty late. And so all of this actually is discussed in a report that Tom and I work on every year. We update it. This year we're calling it A Deep Look at New Memories, and it comes from both Objective Analysis and Coughlin Associates. And the report is now available for immediate download. That you can buy it just with a charge card online. And there are 2 URLs that are in the downloadable slides that you can click on if you'd like to have a look at it. This photograph that we used for this year's report is actually a hole that has been etched into a resistive RAM that was developed by the research firm in France, CEA Leti. So they let us use that for this particular thing. And you can see that bottom little vertical pillar, I believe, is the ReRAM element. All the rest of that above it is the metallization to make interconnects on the chip. So with that, we're going to turn it back over to Arthur. He's going to moderate questions.
Well, thanks, Jim and Tom. Excellent content and information. Very, very, very interesting. So the first question is about SRAM, and why is the scaling of SRAM not keeping up with logic?
This is something that I should know, but I don't really understand. And I've spoken to people who are down in the chip design thing, and they say it's a very difficult thing, but it's got to do with the balance of the pull up and pull down transistors that you have inside the SRAM cell. And apparently you can't balance them without making them extremely large. And so that's what's supposed to be keeping them from moving that way. But, like I say, I don't understand it that well. My understanding is that CFETs may end up changing that, but CFETs are not in widespread enough use yet that people have a really solid feel for that.
Mm-hmm. And what about DRAM over the next 10 years? And why isn't that going to get down below the 10 nanometers that you mentioned?
Yeah, DRAM has a unique problem. It requires a certain level of capacitance, and that capacitance can only be provided by something that's got a very large cell. There is some work trying to change the dielectric materials, although an awful lot of those changes were done in the late 1990s. And so now the things that are left as dielectric materials are things that for some reason get into the way of the semiconductor processing. I believe that it's thermal budgets that, if you end up having to do a really high temperature process after you do is something that's sensitive to low temperatures, then you end up destroying the low temperature part under that. And so my understanding is that that's got something to do with why these new materials can't be used to shrink the capacitor. And so with that, you're stuck with a certain capacitor size. And if you were to have the width of it, then you'd end up having to double the depth. And the industry has problems with actually making the holes much deeper than they already are. They're about a 40-to-1 aspect ratio today.
You know, there's one other thing we probably should mention with regard to this is that DRAM, NAND flash, SRAM, these are all charge storage devices. They retain a charge, and that's how they keep the data. And the charge-based devices can be subject to, if the features get smaller and smaller, you're storing fewer electrons. The problem they ran into with the NAND flash, why they couldn't really go below 15 nanometers. So trying to make these charge-based devices small and get them to be stable, you know, especially if you're trying to make it over a usable period of time, gets to be more challenging as they get smaller. So that's another thing. The other thing, and I know, Arthur, you brought this up with us talking earlier, is that these devices, charge-based devices, are subject to external influences like radiation or thermal environments and things of that sort that can be a challenge as well. So those are other factors, I think, in addition to, you know, the manufacturing and device operation issues, or part of those device operation issues that Jim brought up.
All right, thanks, Tom. Another question coming in about high bandwidth memory and why can that not be made persistent or non-volatile?
Well, you could make it persistent. That's, yeah, you know, if you replace the DRAM chips on it, which is basically all that it is, with an MRAM or resistive RAM or ferroelectric or something like that, then you could have persistent HBM.
Or at least some of that memory, you know, in the stack could potentially be, you know, an MRAM chip, for example.
Yeah. And that does help you with power events, you know, if you have a power failure, but it doesn't really do an awful lot. Well, it would also save some energy because of the fact that you don't have constant refreshing going on with the DRAM. But the HBM in an AI application is always going to be overwritten with a whole bunch of new data. And so the advantage of being persistent is not all that strong in that kind of an application.
And the other thing is that right now, a lot of these emerging memories, they don't have the same kind of performance that you can get with those DRAM chips. And so that's the other factor as well.
So back to a topic you brought up before on the radiation, there's a question about what makes these new memory technologies like MRAM more radiation resistant. I know it could be in the circuitry and the packaging material, but can you answer that question?
Well, Tom actually answered that question. They're all of the existing memory technologies are charge-based to some degree or another. SRAM is less charge-based than the others, but the way that DRAM works is it stores a charge in a capacitor. And when a radiation, an alpha particle or gamma ray or something like that goes through that capacitor from one plate through the dielectric and into the other one, it drags electrons from one plate to the other. It basically performs like an instantaneous short circuit and can disrupt the bit. That same thing happens with flash because in a way the floating gate in a flash chip is like a capacitor. And so electrons can be drained out of the floating gate by some kind of radiation. With SRAM, it's a little bit more, it's a little bit different because you've got the two transistors and both of them have insulated gates on each other or on themselves. And the way that an SRAM holds its data is that as long as this guy's turned on, then it turns this guy off. And if this guy turns on, then it turns this guy off. And if one of them gets into a confused state because of the fact that the electrons are being shifted out of the gate and into the channel, then it ends up that the one that's turning the other one off is going to kind of give up its dominance over the other one. And then you'll end up with a bit that's confused and may end up settling back in the right state, or it may not.
The other thing is that you look at these new memories you're talking about, the non-volatile memories. they essentially are resistive devices. There's a category called resistive memory, and that's certain types of memory. But in almost all of these types of devices, we're looking at changes in resistance. That's how you store the information, and that's less sensitive to radiation, particles going through the device, things of that sort, than a charge-based device where the charge can be basically displaced, by that. So that they're sort of intrinsically more radiation hard than the conventional charge-based memory devices.
Yeah,
Mhm.
yeah. The emerging memories, with the exception of MRAM, they're all moving atoms
Yes.
to,
Yeah.
and so the radiation is not strong enough to move those atoms around. If it is strong enough, then it's going to be a really, really strong field. But with MRAM, then you've got this thing of the two magnets being either aligned with each other or opposed to each other, and you don't have the capability of a radiation changing the direction of magnetism in a magnet.
Yeah, the electromagnetic radiation is not enough for the magnetic component to do anything significant to the MRAM devices. So,
Great. Thank you. So we have a lot of questions coming in. I'm going to
good, good.
3 more questions. If you can answer these succinctly and quickly, we're going to end in about 4 or 5 more minutes. So I'll ask 3 more questions. So the first one is, so I just think of all the investments that's needed from these universities, from companies putting us. I mean, it's not new memory. They've been around for a long time, right? These new memories. So I don't know if there's a new name for them, but is there one that's going to come out of who's going to win this, or is it going to be one or several, or
Well,
that one?
so one quick thing is that there's been, it seems, and probably for Jim too, is that like every month at least there's somebody that comes out, especially from the university, with some new technology where something changes from one state to another, and therefore it's going to be the memory technology is going to displace everything else. So there's been a constant change and development in these areas, a lot of research, a lot of work on these. I think that right now, in terms of actual implementations, mostly on the embedded side right now, that there's a lot with going on with the MRAM. There also is activity going on with SRAM in these devices as well. By the way, there's also standalone MRAM, say from Everspin and Avalanche and other companies as well. So there's developing some applications there. A lot that seems to be going on the embedded side, and both MRAM and also resistive RAM. And right now, those two seem like they are probably the best candidates for these embedded applications, which we believe is going to drive the volume manufacturing up and eventually also lead to development of discrete devices.
Thank you. So yeah, a couple more minutes, 2 more questions. So the first one, I had to bring up CXL and versus low cost memory, and where are these technologies will they have a role with the CXL interconnect standard?
Yeah, they can go into CXL. I wrote a report on CXL, that examines that to a certain degree, and CXL has the capability built into it to support persistent memories and to support memories that have different write speeds than read speeds. All of the things that you need for these, and so it's something that can be done. And then it's a question of, will a market develop for persistent CXL modules, and that has yet to be determined, and whether or not there is a desire, a hunger from the market for CXL modules that today would be more expensive but offer these extra advantages. We'll see what happens with that.
There's one other thing to keep in mind too, is that some of these, so a lot of our processing technology is based on current-based devices. For example, these MRAM devices have an interesting capability, and this could be part of possibly in CXL or other architectures where you're doing processing closer to memory, is that there's a possibility of down the road somewhat, this is probably looking in the 2040s, of having spin-based logic devices in addition to spin-based memory be a possibility, which could have interesting. There's a lot of things going on in getting memory processing close to memory, but it's another thing that could potentially drive interest in these technologies. It's not resistive, and therefore the energy loss from that kind of logic operation would be significantly less. So it would use less energy in doing computation, which could have advantages.
So I have a question about USHVM for embedded memory. I'm not familiar with that. Are you aware of that? Okay. So we will take that question and post it on the SNIA website. We'll do some homework and check and answer that. Let's see. One last question. So RoHammer on MRAM. So why is the MRAM more resistant to the RoHammer issue? If you have that answer.
Yeah, that's something that my understanding of the way that RoHammer works is that because it is adjacent capacitive loads, that the capacitors that are the cells are being hit by noise that's emanating from the adjacent row, that they end up losing or corrupting some of their charge that's on there. And with MRAM, I believe that there might be something where there could be adjacent cell interference, but that's something that so far with the processes that we've seen MRAM on, it hasn't been a problem that I'm aware of.
It hasn't been something that I've seen brought up much yet, but and as things get into wider use and more of this memory being in use, it'll be interesting to see if things like that, if there's an issue also with MRAM. It seems like it might be less sensitive, likely be less sensitive, but I don't know right offhand, the data on that.
Well, great. Thank you, guys. I'm going to wrap it up there. And the next slide here, just a reminder to everybody, thank you so much for attending. And thank you to Jim and Tom for always stepping up on these industry events and these presentations. Excellent presentation, I thought. So everybody else, please comment and put your suggestions and rate it. So we appreciate your feedback. A couple things coming up this summer. We've got the Future of Memory and Storage Conference. We've got the SDC coming up. There's others as well that are not all listed here. SNIA has an extensive abundance of resources online. Please visit us online. And lastly, we encourage you to join SNIA. You can join my persistent memory special interest group. We'd love to have you to continue these conversations and create market knowledge and increase the awareness of all this through presentations like this. So thank you everybody for joining. And again, thank you to Tom and Jim for putting all this together.
Thank you, Arthur. And thanks to the audience.
Thank you. Thanks, everybody.